The Big Bang, the birth of space-time, energy, and everything we know and love about this universe. The Hubble Space Telescope, the human race's celestial guardian, has been spotting unexplained objects speeding into our solar system for the past 33 years. This isn't the narrative of a science fiction movie, but a perplexing reality. It all started in the early 1990s when the mystery of our universe was revealed through Hubble's newly functioning lenses, penetrating the cosmic veil. Weird outliers, like dim, rapidly moving dots that didn't fit the usual description, appeared among the brilliant nebulae and galaxies. At first, these objects were thought to be simple space trash or observational mistakes. However, as they kept multiplying and getting closer to our solar neighborhood, NASA secretly became concerned. The evidence has grown indisputable as the years passed into decades. Are they remnants of an ancient cosmic event, or perhaps artifacts of an alien civilization sending a cryptic message through the void? Join us as we explore the strange objects coming towards the solar system seen by Hubble. A constraint that has dogged astronomers since Galileo's time, Earth's atmosphere was the driving force behind the creation of the Hubble Space Telescope. The visibility of even the most advanced devices located on Earth is limited by the fact that moving air pockets in the atmosphere obstruct and distort light. Astronomers are able to look farther and clearer into the universe with the help of orbital telescopes, which act as eyes in the sky. Although scientists started fantasizing about such a telescope in the 1940s, the Hubble Space Telescope finally brought those dreams to fruition after more than 40 years. The telescope's original October 1986 launch was scrapped after the loss of the Space Shuttle Challenger. The telescope started returning groundbreaking, but inaccurate photographs in 1990, when it was finally operational due to an optical issue. Its pictures were rather hazy, but they were still better than those of instruments on Earth. In December 1993, astronauts from the Space Shuttle Endeavour performed 5 days of spacewalks to repair the telescope in orbit some 353 miles above the Earth. The repair worked, and Hubble began to deliver crystal-clear images. Not long after the fix, Comet Shoemaker-Levy 9 slammed into Jupiter. Hubble captured the comet as it broke up, offering insights into the role comets may have played in delivering water and other material to the solar system's planets, including Earth. Other images of Jupiter revealed unexpectedly low amounts of water in the atmosphere of the gas giant. Astronomers have been able to use Hubble's observations of the dwarf planet Pluto to create surface maps of the planet and even find 4 new moons around the dwarf planet. Hubble's images have also helped to pin down the age of the universe, which the expansion rate of pulsating stars suggests is some 13 billion to 14 billion years. The Big Bang is the most well-established explanation for how the cosmos came to be. The idea behind this theory originated from the realization that galaxies outside of our own are accelerating away from us in all directions, as if they were all driven by a powerful explosion from long ago. The Big Bang theory was initially proposed in the 1920s by a Belgian priest called Georges Lemaitre, who postulated that the universe originated from a singular primordial atom. The idea was given a significant boost by Edwin Hubble's findings that galaxies are accelerating away from Earth in all directions, and by Arno Penzias and Robert Wilson's discovery of cosmic microwave radiation in the 1960s, which they interpreted as echoes of the Big Bang. Updates to the literature have shed light on how fast the Big Bang was. Theoretically, the cosmos was extremely small, less than 1/1,000,000th of the size of an atom in its initial tens of thousands of seconds of existence. Gravity, electromagnetism, the strong and weak nuclear forces, and an incredibly dense and energetic state were supposedly fused into one force at that point. But our present ideas do not explain how this could have happened. We don't yet know how subatomic gravity works, which is a major roadblock to this. It is also believed that the primordial particles were able to blend, mingle, and settle into approximately the same temperature due to the incredibly close quarters. Subsequently, in an incomprehensibly brief instant, the entire mass and energy of the universe expanded outward in a relatively uniform fashion, with minor deviations caused by quantum scale fluctuations. Inflation, a hypothesis of extremely rapid expansion, may account for the uniformity of the universe's temperature and density of matter. The expansion of the cosmos persisted after inflation, albeit at a considerably reduced pace. We still don't know what drove inflation. The stars and galaxies that make up our modern cosmos were formed when a wide variety of particles cooled and expanded over time. By the time the universe was a billionth of a second old, it had cooled down enough for the four fundamental forces to separate from one another. The universe's fundamental particles also formed. It was still so hot, though, that these particles hadn't yet assembled into many of the subatomic particles we have today, such as the proton. As the universe kept expanding, this piping hot primordial soup, called the quark-gluon plasma, continued to cool. Some particle colliders, such as CERN's Large Hadron Collider, are powerful enough to recreate the quark-gluon plasma. Antimatter, which is identical to conventional matter except for its opposite electrical charge, could be created when matter and antimatter particles collided in the early cosmos due to the extremely intense radiation. The amount of matter and antimatter in the early cosmos was believed to have been equal. Photons used to be powerful enough to create matter-antimatter pairs, but that all changed as the cosmos cooled. Consequently, several matter and antimatter particles coupled off and destroyed one another, much like an extreme game of musical chairs. Life on Earth, as well as planets and galaxies, are composed of the leftover materials that managed to survive. The fact that we exist demonstrates unequivocally that antimatter and matter are subject to somewhat different natural principles. This rule imbalance, known as CP violation, has been observed experimentally by researchers. Physicists are still trying to figure out exactly how matter won out in the early universe. The residual matter merged into the familiar nuclei of atoms, protons, and neutrons during the first second of the universe because the temperature was just right. The protons and neutrons had gathered into nuclei of hydrogen and helium after the initial 3 minutes. The early cosmos was too hot for electrons to settle around atomic nuclei and create stable atoms. Even if they did exist, the universe's matter remained an electrically charged fog that was so dense that light had a hard time bouncing its way through. The formation of neutral atoms, a critical event known as recombination, would not occur until the cosmos cooled down sufficiently, which would take another 380,000 years or more. The cooler universe made it transparent for the first time, which let the photons rattling around within it finally zip through unimpeded. The cosmic microwave background radiation that we observe today is a remnant of this primordial afterglow. A lot of the radiation is the same as what TV antennas use to send signals. However, this radiation is the oldest of its kind and could reveal a great deal about the early cosmos. Even after the Great Bang, almost 180 million years later, the cosmos was starless. In that amount of time, stars were formed when hydrogen clouds were pulled together by gravity. The initial galaxies and stars were likely supported gravitationally by enormous clouds of dark matter, an as yet undiscovered substance that weighs more than 5 times as much as visible matter. The ionization of neutral atoms occurred when the first stars burst into existence because the light they released was powerful enough to take electrons from the atoms. A group of Australian researchers said in February 2018 that they might have found evidence of this cosmic dawn. By 400 million years after the Big Bang, the first galaxies were born. In the billions of years since, stars, galaxies, and clusters of galaxies have formed and reformed, eventually yielding our home galaxy, the Milky Way, in our cosmic home, the solar system. The expansion of the cosmos is ongoing, and, much to the amazement of scientists, is speeding up. Some believe that dark energy, a force that defies gravity, is responsible for this acceleration. Although its exact nature remains a mystery, dark energy is believed to account for 68% of all matter and energy in the cosmos. Dark matter makes up another 27%. In essence, all the matter you've ever seen, from your first love to the stars overhead, makes up less than 5% of the universe. Nearly all large galaxies are thought to also contain supermassive black holes at their centers. In our own galaxy, the Milky Way, the Sun is just one of about 100 to 400 billion stars that spin around Sagittarius A, a supermassive black hole that contains as much mass as 4 million suns. The more space we explore, the more galaxies we find. A study conducted in 2016 came to the conclusion that there are 2 trillion galaxies in the observable universe. Even though our Milky Way galaxy is very similar to some of those other systems, others are completely different. We didn't know about galaxies apart from the Milky Way until the 20th century. Older astronomers had called them nebulae because of their fuzzy, cloud-like appearance. But astronomer Edwin Hubble proved in the 1920s that the Andromeda Nebula was actually a galaxy all by itself. Because of its great distance from Earth, it takes light from the Andromeda galaxy, over 2.5 million years, to reach us. Andromeda is the nearest big galaxy to our Milky Way, and its brightness makes it visible to the unaided eye in the northern hemisphere despite the enormous distance. With the introduction of his classification system in 1936, Hubble distinguished between spiral, lenticular, elliptical, and irregular galaxies. Of all the galaxies that have been discovered, spiral galaxies make up over 66%. The flat, rotating disk of a spiral galaxy is encircled by spiral arms that radiate out from the galaxy's central bulge. The matter in the disk may assume a unique spiral shape, resembling a cosmic pinwheel due to the spinning motion. A starry bar runs down the middle of our Milky Way, as it does in all spiral galaxies. In terms of shape, elliptical galaxies are just what they sound like. They're mostly spherical, but some can be so elongated along one axis that they resemble cigars. Giant elliptical galaxies, the biggest known galaxies in the universe, can have a diameter of 2 million light-years and contain as many as 1 trillion stars. Diminutive elliptical galaxies are another kind of elliptical galaxy. There are a lot of older stars in elliptical galaxies, but not much dust or other interstellar material. Like stars in spiral galaxy disks, their orbits are wildly erratic, but they nonetheless circle the galactic core. We know that elliptical galaxies do not produce many new stars. They are common in galaxy clusters. Lenticular galaxies, such as the iconic Sombrero Galaxy, sit between elliptical and spiral galaxies. Their name comes from the fact that they seem like lenses. Similar to spiral galaxies, they feature a central bulge and a narrow disk of stars that rotates, but they lack spiral arms. Similar to elliptical galaxies, they tend to originate in areas of space with a high population density and contain minimal dust and interstellar materials. Irregular galaxies are those that do not fit the typical shape of a spiral, lenticular, or elliptical galaxy. A common reason irregular galaxies, like the Milky Way's neighboring large and small Magellanic Clouds, look distorted and formless is because they are subject to the gravitational pull of nearby galaxies. Their abundance of gas and dust makes them ideal sites for star formation. It is more common for galaxies to be found in bigger groupings, like groups, clusters, or superclusters, yet occasionally they may be found alone or in pairs. For example, the Milky Way is one of several galaxies that make up the local group, which spans around 10 million light-years and includes the Andromeda Galaxy and its satellites. Within the Virgo supercluster, a concentration of galaxies that extends around 100 million light-years across, are both the local group and the Virgo cluster, a nearby galaxy cluster. Meanwhile, researchers identified the Virgo supercluster in 2014 as a branch of Laniakea, a larger supercluster consisting of 100,000 galaxies. Clusters of galaxies engage in a celestial waltz of gravitational interactions, which can lead to galaxy mergers. Gases can be pushed toward the galactic center when two galaxies merge and collide, which can cause things like fast star formation. Thanks to Hubble, we now know that the Andromeda Galaxy is going to smash into our Milky Way galaxy very soon. The two will combine in about 4 billion years, according to astronomers who measured the tangential velocity of the approaching Andromeda Galaxy. Turning Hubble toward galaxies with lengthy gas and dust tails, remnants of mergers helped scientists uncover characteristics of these objects. By exploring these collision centers, the Space Telescope discovered a new type of massive, brilliant star cluster. About 13.8 billion years after the Big Bang, the first stars in the universe began to explode about 180 million years later. The early galaxies were already shaped by gravity when the universe was just 400 million years old, which is less than 3% of its present age. Modern astronomy suggests that, with a few probable exceptions, the vast majority of galaxies have massive halos of dark matter surrounding them. Additionally, theoretical theories imply that the initial galaxies were formed when normal matter was gravitationally supported by enormous filaments of dark matter in the early cosmos. The formation of galaxies is still a mystery, though. Some think that galaxies evolve from globular clusters, which are smaller collections of stars, and others think that galaxies came first and then gave birth to globular clusters. Determining the proportion of stars that developed in a particular galaxy from its own gas, as opposed to stars that formed in another galaxy and subsequently joined the festivities, is another challenging task. The Hubble Space Telescope played a key role in the identification of dark energy, a force that opposes gravity and adds to the universe's continuous expansion. This force is little understood but pervasive. By measuring the atmospheres of planets outside our solar system, Hubble investigates their compositions and collects data that may one day help in the hunt for life beyond Earth. This remarkable instrument has been providing scientists with invaluable data and insights for over 3 decades. Despite its advanced years and the many problems it has encountered with gear that has been in orbit, Hubble can see far beyond Earth's atmosphere because of its low Earth orbit, which allows it to peek into space directly. Because atmospheric water vapor does not distort its measurements, it is able to perceive extremely faint and faraway objects. To examine objects in the visible light wavelength, Hubble employs spectrographs in conjunction with its 2 primary camera equipment, the Advanced Camera for Surveys and the Wide Field Camera 3. This enables the spacecraft to collect data on a diverse array of targets. Hubble has given data to over 19,000 peer-reviewed articles and made over 1.5 million observations over its career, according to NASA. Astronomers are still using telescope data to learn more about the cosmos, extrasolar planets, and planets like Earth. In its 33rd year in orbit, the venerable Hubble telescope continues to provide invaluable insights, as demonstrated in a video published by NASA. One reason Hubble is well known is the stunning photographs it has captured, especially of the planets in our solar system. The unusual rings of Saturn make it one of the most visually striking planets, and Hubble was able to record observations of a structure known as spokes within these rings. These irregularities, which resemble shadowy splotches on the rings, manifest at specific seasonal intervals and are believed to be connected to the planet's magnetic field. The spokes will be easier to see in 2025 as the northern hemisphere of Saturn nears the autumn equinox, allowing astronomers a better chance to analyze them. Another set of images from our solar system taken by Hubble was used to analyze the changing seasons of Uranus and Jupiter. Like Earth, other planets in our solar system also have seasons due to the tilt of their axis, with one hemisphere pointed more toward the sun and therefore being warmer. However, different planets have seasons that last for different amounts of time than the seasons on Earth because of the length of their orbits. Hubble observed Jupiter's northern hemisphere storms through its telescope, which occasionally congregate into cyclones and anticyclones that round the planet in a unique wavy pattern. Then, turning to Uranus, Hubble noted the yearly changes brought forth by the planet's acute tilt. It lies nearly fully on its side. This tilt causes some regions of the planet to experience decades of cloud cover, which in turn influences the frequency and severity of storms, especially in the polar regions. By monitoring the stars that exoplanets orbit, Hubble is able to identify them. Planets are typically too weak and too small for Hubble to detect directly, but when a star's brightness decreases, scientists can deduce that planets are there. The light from a star dims slightly as a planet moves in front of it. In order to learn more about the planet's characteristics, scientists keep an eye out for these dips. We now know that two exoplanets, Kepler 138c and Kepler 138d, are probable water worlds. Hubble utilized this method to observe them. Given their size and mass, these planets could be ocean worlds very different from any planets in our solar system, as water seems to make up the majority of their composition. Recently, Hubble helped survey galaxies that existed when the universe was only 600 million years old. Previous estimates had suggested that galaxies didn't form until the universe was at least 2 billion years old. The instrument's images have helped scientists understand how galaxies evolve. Hubble also helped turn a staple of science fiction into science fact. When massive stars reach the end of their lives, they explode in a fiery death known as a supernova. The heavy elements formed in the star's core are blown out of the galaxy by these intense explosions, which may also produce black holes or hypercompact neutron stars. Scientists now have a better grasp of the supernova process thanks to Hubble. One supernova that burst 3 years prior to Hubble's launch has been captured in its images ever since the observatory started taking pictures of the cosmos. Over the years, Hubble has taken countless images of the supernova, allowing scientists to piece together its evolution. Eta Carinae, a star that seems to be exploding, is another object that Hubble has spent time analyzing. Thanks to the telescope, researchers have been able to examine the peculiar object up close, learning about its structure, and even finding evidence of the dramatic eruptions it has endured over the past 2 centuries. In modern times, the Kepler spacecraft, which searches for exoplanets, is perhaps the first instrument that comes to mind when discussing such celestial bodies. However, the first image of a planet in orbit around another star, Fomalhaut b, was taken in 2008 by Hubble. Before that, Hubble assisted in the discovery of 16 planets that might be in orbit around other stars by tracking the dips in starlight as each candidate planet moved past Earth. Research into the atmospheres of faraway planets has also benefited from the device. Hubble prepared the way for Kepler, although in a roundabout way. The vastness of the cosmos was unveiled by Hubble, who discovered billions of stars that might be home to planets. Plus, launching Hubble into orbit proved that a certain threshold of technological proficiency had been reached. Even more astounding is the fact that astronomers believe they have found a black hole accelerating away from the center of a faraway galaxy. With a mass equivalent to the Sun, a narrow line of newly formed stars, some 200,000 light-years long, is being left behind as the supermassive black hole rips through intergalactic space, squeezing the sparse gas and dust that is accessible. Despite its thinness, the black hole is roughly half as bright as the galaxy it traces back to, due to the abundance of hot blue stars in its stellar trail. From what we can tell, the 3 supermassive black holes that were engaged in the 2 galaxy mergers probably danced their way to the point of ejection, sending this black hole hurling through space. Should this be verified, it would provide the initial empirical proof that the ejection of supermassive black holes from their host galaxies is possible. Even while black holes don't actually produce any light, they frequently leave behind telltale signs of their presence. One example is the presence of dense rings of superheated gas and dust around numerous black holes. The presence of a black hole can be confirmed by the abundant light emitted by such accretion disks. However, this black hole wasn't revealed by an accretion disk. It was the unusual linear streak seemingly linking it to a nearby galaxy, which Van Dokkum first noticed in an image captured by the Hubble Space Telescope. He and his team later confirmed the streak was indeed linked to the galaxy, with follow-up observations taken with the Keck Observatory in Hawaii. Astrophysical jets are a typical explanation for such streaks, so the researchers also looked into that. The black hole core of the neighboring galaxy might possibly be the source, but the streak becomes more prominent as one moves away from the galactic center, and it doesn't fade out towards the end. So astronomers think it's a trail of newborn stars. At the outer tip of the streak, where the suspected black hole is thought to be, the researchers also see evidence of a shock wave in front of the black hole. How it works exactly is not really known. According to the astronomers, this rogue black hole was probably kicked out of its parent galaxy during two different mergers that occurred not long ago. Supermassive black holes from two galaxies would have merged for the first time some 50 million years ago, causing them to enter into orbit around each other. A subsequent merger with a third galaxy set the three supermassive black holes into a tumultuous dance, which eventually resulted in the complete ejection of the single black hole from the system. The group also believes that the other two binary black holes should have been ejected in the opposite direction from the solitary black hole. The next step for the team is to gather further observations using the Chandra X-ray Observatory and the James Webb Space Telescope to verify this theory. These are just a few of the scientific discoveries Hubble was responsible for in its 33rd year. Additionally, Hubble witnessed the DART spacecraft impact after it purposefully collided with an asteroid to redirect its trajectory. This was an exercise in planetary defense designed to test our capabilities in the event that we detect an asteroid threatening Earth. Thanks to Hubble, we can observe the after effects of the hit and gain a better understanding of what transpired. The Hubble Space Telescope is undeniably a highly visible scientific endeavor by NASA, having attracted consistent public interest throughout its entire lifespan.